Hello there, this is Universum, the place where you learn about the entire universe. Today we're going to be talking about black holes, why they exist, and their pangs on the space and time as we know it, based on the Einsteinian revolution. Now, just a disclaimer to all of you guys who don't like watching long videos, this is going to be quite a long one, so if you guys don't like long videos, then click off right now. So anyways, if you're still here then this is what I got for you. We know a lot about immense objects called black holes. Over history, they have been named a variety of items. Black body stars, great voids, and so on. But what do we know about these strange objects? How strong can they be? And how do they even exist? There is one feature that makes black holes different from the rest of the universe, and it is their event horizon. The type of space that is outside of the black hole that truly separates the universe from the black holes. Black holes are clumps of gravity that have the power to rip stars to pieces. They are pieced together, possibly by the Einsteinian revelation due to them curving space and time infinitely, but this is also the reason why they don't relate to the Einsteinian revelation, which we'll get onto a little bit later in this video. Black holes have a violent past, but let's look at them visually. Why are black holes so different? Their dense past says it all. Get it? Let's look deep inside the core of a black hole, or, well, at least what we think is the core. There may be no core, there may be a singularity, there may be an Einsteinian rows and bridges. Who knows? We cannot look at this area of space, for this region of space is so small and dense that we are not able to look at this one. If you want to know how small I'm talking here, let's just say it's infinitely small. It's a singulative point. It has 0 dimensions within it. So it is combined together. Now this also creates the Hawking revelation as well. Yes, what Hawking thought of when he was in his early 20s is that he thought of a theory where the universe was a singularity itself. It was singulative, it came from a point. And that our universe could have came from a black hole. And then, he developed mathematics although he quickly dropped the theory. Anyways, so these singulative points are so small that they break the laws of gravity and nuclear physics itself. This is why you cannot interact with the Einstein revelations, and how are we supposed to measure an object that has infinite curvature on the space and time plane? The Schwarzschild brain. You can't. It's infinite. This is why we made loop quantum gravity. Loop quantum gravity, what it is that so it has loops and nodes that are connected to one another as sort of like fiber-like clutches that are connecting to one another. They are far smaller than the Planck scale, but they help us measure the curvatures of black holes themselves much, much clearer, rather than just infinitely small times infinitely small. Basically, it is a revelation times a revelation. Like all you're going to get is a nonsense Taylor group, which is not going to make any sense to us. So, why are these objects so heavy? And how do black holes come to be? It all starts with light. Light meaning stars, massive ones, hundreds or possibly even thousands of times the mass of our sun. These massive behemoths are solar system-wide monsters that have a very unstable life. These stars harass and abuse the poor planets around them. Any life that these stars were not meant to last. Any life that were on these stars. Although there are some stars that in the past that looked like they had life around them. All that's it was because of the strong radio bursts that are coming out from solar flares and sunquakes. Since these stars only live for about a few million years, it is a blink of the eye in the universal scale. In fact, one of the largest stars in the universe would be a supergiant star, which is still in its main sequence stage, actually. Due to it being so massive, this star is named R136A1. It is an extremely massive blue star. It is so massive that it has condensed itself and is currently releasing about 300,000 tons of material off of it and creating a sort of halo accretion disk around it. When the helium fusion is exhausted and gravity wins its radiation pressure and crushes it inside harder before it to use heavier and heavier elements to counteract the gravitational pushes and shoves by gravity. Then it releases more radiation before then it swells into even larger sizes. And then they fuse heavier and heavier elements as helium turns to carbon, carbon turns to oxygen, oxygen turns to neon, neon turns to silicon, and silicon turns to iron. And then death. Iron is nuclear ash, cannot be fused. This means the star has only one thing left to do, is collapse. What happens next is fascinating and awesome. Particles like the nucleus of an atom, the quarks around them, gluons, etc., surrounding them really don't want to be near one another and keep their difference due to the position of one thing called the Higgs boson. The Higgs boson would be the weak force, as well as weak gauge bosons is also another thing. And then the thing that keeps the quarks together would be the gluons that keep them together, which would be strong force distributors. But since because the immense star pressure of the collapsing stars, it provides so much force that even more than the decoseptoctillions of Higgs bosons inside of this massive star, maybe even more, and then electrons surrounding the atoms get crushed and turned into neutrons, due to them creating more and more mass. And neutrons are heavier than protons, so they get crushed into them, and then the quarks that are inside them, what happens next, that's they turn into heavier and heavier quarks, like strange quarks, charm quarks, top and bottom quarks. By the way, fun fact, top quark would actually be the most massive quark there possibly could be. All right. Even more than the heavy nuclei and the emptiness inside of atoms is suddenly filled with smaller particles. Well, of course, they're the quarks, of course. They really want to be near one another due to them being held together, being confined by the gluons. They desperately push back in order not to get crushed by gravity. They push it back by the radiation that's being emitted from them. And then these higher and higher density, like a top quarks, which is about 127 micro electric volts. Yes, that's how I measure different types of particles. They push back against it in the form of radiation. They release alpha and beta particles. Well, not necessarily alpha particles, but more beta particles and tiny, tiny little neutrinos are coming away from it, along with some photons. If gravity wins this insane battle, then this object will become a neutron star. It'll become a black hole. But the subatomic particles win, or even the elementary particles win, they'll become a neutron star. Insanely dense object that is just barely a star at all. Then the dying star explodes at about 25% the speed of light. All this gets bounced off of the iron core, and then makes it even stronger, creating a weird region called nuclear pasta. Yeah, and yes, this is actually what it's called. This strange nuclear pasta is a fusion crust is around the star that is condensed iron that has such short ions together that they're literally touching one another. It's really hard to see how small the ions are even. All this gets, and then the most bright event in the entire universe of a huge star. Then the entire star collapses and then turns into, as you know it, a supernovae. Although there are also different types of supernovae. Like, for instance, there's a type 1, type 2, and type Ia supernova. And then there also are novae and outbursts. First, let's go look at an outburst. An outburst basically is what happened with V838 Montesideris. This is a star. This was a supergiant star. It was a supergiant red star and a smaller blue star. What happens is that then in 2002 they collided with one another. They create a spectacular image. You'd expect these stars to simply explode and then just leave behind a black hole. But no, it was just below the threshold value for the star not to completely collapse and turn into a black hole or neutron star. Instead, the star survived and turned into a red hypergiant star. Literally the largest star we possibly even know of. In fact, the largest star in the universe is actually a red hypergiant, which would be Stephenson 218. Now Now, do this thought process with me, although. Can we see a black hole? Think about it. We have a telescope and a very crude image quality. But how can we not see a black hole brighter than billions of stars that is feeding into its accretion disk? That, although, even though the black hole still does, it literally absorbs everything, the accretion disk, as in supermassive quasars, and even the blazar bursts that are coming out of it, can we see it in visible light instead of just in X-rays and radio waves? Anyway, that is a simplified and shorter version of a black hole amazing image quality without going to have to look in different other types of light on the light spectrum. Here's what you have to do: gravitational lensing. Gravitational lensing is when a massive object passes in front of another object, and this creates a halo around the object in front of it and magnifies the object behind it. This makes the photons that pass through the halo turn shorter and higher power wavelengths it turns lower wavelengths to shorter, much more powerful wavelengths. It's due to the probability densities, as we can see inside the infinite square well. Well, of course, there is a velocity vector to that is right there. The velocity vector would then rotate around an axion. And then what happened next is that then there will be different states that then they go all the way up to 9 states. And then they go up. So the first unstable state would be represented as sort of sine wave like form. And then they go up to multiple sine wave forms as their probability amplitudes start getting shorter and shorter. And then the phasors get higher and higher of the objects. This magnifies the object and makes, to much more powerful wavelengths. This amplifies the photons that pass through this bright halo and lets us see and lets us get away and much often more defined images. Either way, they are very close to, they are either far away or very close to us, a few light years. They can still allow us to see in definite detail. In fact, even the farthest away galaxy ever seen in the entire universe was in fact a gravitationally lensing event. Now what happened is that, this galaxy was called GNZ11. Now this galaxy was over 30 billion light years away. Now you're probably wondering, how is this possible? As Einstein said in his general theory of relativity, well, this would be literally impossible due to time and space are linked together. They'd be relative to one another. They would share the same exact symmetry with one another. So then how would this be possible, you may ask? Well, the truth is, nobody knows. Although we do have theories on it, but they're not necessarily quite proven now. Anyways, so then what happens when we put a very massive object in front of a very massive object? Now let's wonder. Would it just magnify the object behind it as it odds of the magnitude, and will the photons just not come to right of our eyes in such short wavelengths that they blind us or even just go unnoticed? Nobody knows what would happen in this event. There have been probably have been science in the past or present that's pondered about this cosmic query. But as never been answered, perhaps the mischievous little photon fools again, and it's playing tricks in the Schrodinger equations. Perhaps there is a different theorem in the future. There is yet another question to be asked about black holes that our minds can't comprehend. And it'd be scary if it were true. So scary, in fact, that we may even have to change our perspective of reality. Are we inside of a black hole? And are there other baby universes in the form of Calabi-Yau manifold spaces that exist in this truly strange and dark space-time? To understand if we are inside of a black hole, we first have to look at the ones we already know to exist. Let's look at the most well-known black hole first, which would be Sagittarius A. It's at the center of the Milky Way. And, of course, well, quite obviously, it is in the constellation Sagittarius. let's use this well-known black hole later in this speech, as we have another topic yet to talk about. Information and everything it has in it. You might think of information as ones and zeros on a computer screen, and if you don't, then good. I'm glad we're on the exact same page. Getting back on topic, information in astronomy simply is the astronomy and physics is simply the way atoms are arranged, and where are these atoms, and where are they in the past or present, and possibly even on different types of formalisms, as we can see based on the Einsteinian revolution. Let's make a well-known example with carbon atoms. Arrange them one way and you get graphene. Arrange them another way and then you get graphites. These they're very similar materials. In fact, they're pretty much the exact same thing. What changed is their information. Simply graphene is basically this graphite, except stretched out to extremely long and small sheets, literally an atom wide, so literally an atom thick. Well, graphite, as seen in this pencil right here, that basically is graphene, but stacked up in sheets, and then makes it very bendable and weak. Anyways, Alright. Other than having extremely similar names, they're virtually made of the exact same material. The thing that changed is the information in the atoms. Are inside these two different types of materials. Information tells us what is different about objects in the universe. If you were to take every single atom, wave of radiation, dark matter, dark energy, and elementary and subatomic particle in the universe, you could theoretically read the universe right back to the Big Expansion. The information of atoms and everything in the universe is traceable all the way back to the fiery creation as we know it. You and me, your house and your pet, if you have one, of course. And every single photon, atom, quark, proton, neutron, loop quantum gravity, string vibrations, Pavan particle as we know it, is made out of the exact same information, traced back to the first three elements: hydrogen, helium, and lithium. And this is where Stephen Hawking's theorem of black holes screwed us up. See, since when Stephen Hawking was a scholar, and what he did is that so he thought of a theory of black holes, and other than a singulative point of the universe, he said, what if we could apply Penrose's theory of black holes to the information of the universe? What would happen? Well, in theory, what would happen is that anything goes inside the black hole, they'd be destroyed. They would be encoded on the event horizon of the black hole. If it possibly is possible. Now, information is what makes everything different in the universe. But while black holes, they grind it down, so we don't know what the strange object is that goes to the black hole that creates the information paradox, and this is a big problem. This means that black holes could literally get rid of the universe itself. This could literally mean that the universe has a self-destruct button, and it's only waiting to be pressed. Well, honestly, there are different approaches to this theory. There are more. Some people think there's 3, some people think there's just 5. There are many different types. But in this video, we're just going to be talking about one of them, which is going to be the universe is not necessarily lost, and it is safe after all. We know that black holes swallow the information and eventually destroy it or delete it later. But have you ever thought about what black holes do with this information? Since if black holes just capture the information in the form of radiation and then give some off in the form of Hawking radiation, well, they don't necessarily give it off, but they more give it off in the form of entanglement. There are 2 different types of particles that are formed in our quantum furnaces. And then these 2 particles, which is a particle and a particle. So you got something like a electron and a proton, or a tau antineutrino or a muon, and then they just would be collide with one another due to them being entangled with one another. It doesn't really matter what combination you have. It simply just matters if they're entangled with one another and if they're of the exact opposite charges from one another. As Newton said in one of his laws, which would be the 3rd law of physics, He said that every action has an opposite and equal reaction. The black hole have, anyways, this would be called Hawking radiation that is formed. And the strange thing about, but the reason why we hadn't necessarily wondered how entangled particles do exist and how they interact with one another is that well, entangled particles, they can be entangled literally over anywhere. They can be entangled even in the past. Like, for instance, if you were to use the Einsteinian revelation, and then if you were to put one particle at one end of the universe and another particle at the other end of the universe, they'd be in different times. But yet they would still be entangled with one another. One is in the past, and one is in the past. So anyways, the black hole would have never been discovered due to all these objects, due to the laws of gravity and physics. But what do we really know how black holes store all this matter information? What is the black hole's version of their hard drive? This is what I like to call the celestial hard drives of the universe. This means that black holes, they harvest all their information, they speed it up to light-like speeds. They stretch it down to an infinite amount of distance, not length, but they stretch it out to a one-dimensional like line that goes on infinitely. Now this line, in fact, that actually expresses one of my theories, is that this line could mean the meaning of the CMB. Due to this being stretched infinitely long, this could be a very strong radio burst signal. And then what this could mean is that, well, since because it is infinitely long, this would provide a lot of background radiation when you think about it. Anyways, this we have the infamous known object known as the Singularity. Let's make experiments. Let's say you don't want to do the dishes, so then you stuff your kitchen to the brim with dirty dishes, while buying more, of course. The more dishes you put in the kitchen, and the more the kitchen gets filled up. At some point, the kitchen is full. Not a single spoon will fit in the kitchen. But then if you use a lot of violence and force to the kitchen, it will collapse and turn into a black hole. Well, of course, it won't. Simply, just all the dishes will break as a domino effect. But let's just say that just for the sake of this argument. The kitchen has the same amount of surface area and the same mass. This means that stuffing more dishes in there is still impossible. So what happens if you stuff more dishes to the kitchen? The kitchen gains more surface area and gains a bit more mass. This means that the kitchen black hole brain. That this is how black holes work. Black holes store the information encoded on their surface. They encode the information on their surface area. They encode it on their outer rims. Now, one thing that we have to talk about is how they do it and what is possibly even the equations behind this. Now, this actually was one thing that Stephen Hawking has done in his equations. Now, of course, he did them in the form of invariant equations. And this actually is one of the first ways how he actually shed some light on loop quantum gravity and the curvature of space and time. And possibly even loop quantum filaments and them being connected to one another and them being fed into the black hole in the form of Judas-Ging completion. So anyways, unbelievably small to a pixel. This creates a possibility. If this is true, then this means that the Hawking radiation coming out, it's not to come off from the black hole, but being absorbed by the black hole in the form of quantum fluctuations. When one particle falls into the black hole, even though it's still entangled with one another, the other particle will be left without a particle to annihilate. This appears as radiation coming out from the black hole, and based on quantum physics, this particle does not appear as radiation, but the Hawking radiation can read the information, and it can carry the information with it. As it escapes the black hole, this may apply for the whole universe and everything in it. This means that everything literally will be encoded on one particle. This is an extreme scientific breakthrough. This means that this could mean one thing. The universe is a hologram. You and me, everyone you know and love in it, is a hologram. Well, not necessarily so as you might think of it. This is good and bad part. The good part is that since because the universe is a hologram, this means that there's no reason for the information paradox to exist due to it all being encoded on the black hole. The information paradox is, well, dead, in a sense at least. This still means we have to change our perception about the reality that we are holograms in a fake universe. We might just be random bits of information stretched on a flat two-dimensional surface and then encoded in the form of three-dimensional Schwarzschild brains. Or both of these theorems might be wrong, and we're looking at this the wrong way. Rather, if we're a hologram or not, we still have to keep on pondering about our questions about the universe. I know we will, but there is another question to be asked. I threw a lot of complex topics at your disposal, but here is one thing I'm wondering about. If you could steal the energy that I talked about, imagine the damage and power that you could behold within the laws of physics. Well, you wouldn't need to imagine any further. These will not become possible until we're at least a type 3 civilization on the Kardashev scale, stealing energy from a black hole. So remember how I said that Sir Roger Penrose, well, he's the one who theorized the black holes? Well, he also is the one who theorized energy states, how we could get it off from the black hole. So how do we steal this type of energy from such an object? Well, as far as we could tell, only on paper. So there are some theories how we could steal energy by rotational energy from black holes, and even the angular and even linear momentum if they are on cross-Christ orbits. And when a massive star dies, they rotate on axis. And the fundamental law of the universe is that, well, things that are spinning don't necessarily want to stop spinning. When an object is smaller, it spins faster and faster and faster, like spinning in your desk chair. This is called the angular momentum. So like, for instance, right here. Right here, I'm traveling at a constant angular momentum. This angular momentum will then be theta. Theta will be a random angle check based on the angular momentum that I am traveling at. Now, this means that basically this also would apply into Newtonian theory. So the amount of force that I apply to it times the mass of the object that is going at. So in this case, it'd be 90 pounds. And then while the force that I'm applying to it probably be about 3 pounds of force. And then this would be time the acceleration of the object, which basically just means how much of an arc second you actually can go around a pivot point. So I'd be the pivot point, I'd be the center of gravity, and then this means that the acceleration would be about a few arc seconds. Anyways, although if you push let's say if I were to pull my arms inward, this is a little bit of an experiment right here. I spin faster. Due to my surface area getting smaller, the value of theta becomes less and less of a constant and more of a fluctuation. So if you pull your arms inward, and then as your arms ascend towards the center of gravity to your torso, the same thing happens when a star dies, although without the arms. Its core, as it starts collapsing, gets smaller and smaller, and its angular momentum in the form of theta spins faster and faster and faster, inevitably fast. Some spin millions of times a second until they collapse to a black hole. And the black hole still keeps its speed, and it spins inconceivably fast. But then, so why does this make some black holes special in some cases? These ringulating black holes, for instance. These types of black holes tend to carry a lot of energy, and there's a lot of energy to steal. At the center of the black hole, there's a point in space, as I said earlier today, that would be a singularity, an infinitely small point containing all the black hole surface area and surface tension along with it. Now, due to it being infinitely small and also infinitely dense, in fact, this actually is one thing that Sir Max Planck explained in his equations, that if anything is smaller than a Planck length, well, in this case, in our universe at least, since due to us not being in a Calabi-Yau manifold space, it would be about 1/16 millionth of a yectometer. And as a spinning black hole, is of course spinning, and points cannot rotate at any axes. So the singularity cannot be at points. Instead, it is a ringularity. Although I do not agree with this theory, since then again, well, wouldn't this kind of defy the laws of black holes then? Since this is that, well, it would still be a singularity. Since because, well, it is smaller than the Planck length, as Planck said in his law, it would still be infinitely dense and small. So it would not be able to create a ring, and a ring still has surface area. Thus, meaning that this is resolved almost. But then again, who knows? I could be wrong. So just please don't take my word for it, okay? But that is what I think on it, based on what Sir Max Planck said, unless someone disproves Sir Max Planck's theory. Anyways, now instead it is a ring singularity of a Kerr black hole, that's what it's called. It is a ring with a thickness of 0, containing all the black hole's mass, with yet again no surface area, which is sort of odd, as I explained before. This makes a very weird and interesting part of the black hole, since it's spinning, called the ergosphere, which envelops the black hole along with the black brain, which we're going to be talking about a little bit later. If space-time are completely broken inside the event horizon, then the ergosphere only half breaks space and time. In the ergosphere, nothing makes sense. In fact, it is possible to enter it and then leave it again, although you might not come out in one piece. The ergosphere is bursting with energy. One way to get this energy is called the Penrose process. What we do is that we send a fast object going at a fast speed, a constant velocity, and then we send it into the fast-spinning black hole. Of course, this is actually quite a silly idea until you actually think about what I'm about to say. The rocket will then go into the ergosphere. Okay, anyways, and then it will go into the ergosphere. And then what it'll do is that, then the rocket will be spinning very fast around the ring singularity, hypothetically at least. And what we'll do is that then we'll fire the rocket relative to the direction of the black hole spinning. And then what we'll do is that the faster we spin, the more energy we'll get. Until we get so much energy, we leave the ergosphere, and our value of theta completely just breaks. And then we give the black hole some mass energy, and the black hole gives us some rotational energy. It's not a fair trade, but it's more of a wager. Then we leave the black hole, and then the black hole slows down just a little bit by an extremely small pixel. But anyways, so then there's even better way to steal energy from a black hole, and oddly enough, it creates the most dangerous super weapon in the entire universe. It's called the black hole bomb. It's very simple how it works. All you need to do is just take a fast-spinning black hole and put a very big mirror. Depending on the size of the mirror has to completely envelop the black hole, proportional to the black hole's size. Well, at least to its size of its event horizon. And the mirror will work a little bit like a Dyson sphere, a megastructure that takes the energy of an entire star. Although our mirror will be way easier to build due to black holes are way smaller and much, much more compact than stars. The mirror's job will be to reflect. Anyways, so the mirror's job will be to reflect the photons from mirror to mirror based on slanted positions. This mirror structure almost will look like a geodesic sphere structure. What will happen next is that then, as these photons get reflected around, then they'll get stronger and stronger as they go around, and they'll just get amplified by the ergosphere due to, as I said before, gravitational lensing. As every single one goes around, it will get stronger and stronger and stronger. If we open up a few panels in here, we will get this strange, weird event that's called super radiant scattering inside of it, which basically is a name for bouncing around between the mirror chamber and the black hole and getting stronger as it gets reflected or refracted around the black hole. And when they are super radiant scattering, they get stronger as they pass. But we can collect this energy by shooting. We can be shooting waves that are proportional to these waves, but then they are oppositely charged from them, because opposites attract into the mixture and then collect the energy as it grows. This energy coming away from the black hole could then be, in theory, an endless source of energy for quadrillions of years, or we could blow it up. If the waves are not released or captured by some other source, they'll keep on getting stronger and stronger and stronger until they shatter the mirror in a hypermassive explosion, ever created by a civilization. The joy in pondering all these questions is that they are not science fiction, and the far future is maybe the only way to survive as we may know it. While all the black dwarfs will burn out, and all the white dwarfs has turned to black dwarfs, then the universe will become dark. There will be nothing around you. Even as Einstein says, relativistic theory, well, you'll not be able to tell if you're moving or not. Instead, you'll just feel like that, well, you're not going anywhere. The farther universe will be a very dangerous place because there may be millions and millions of black holes zipping around everywhere and nothing there to light their accretion disks up. But there is yet another question to be asked while staying on this topic. How do black holes influence string theory so much? And why do they have black brains? String theory is a possible theorem for the nature of everything. But what string theory means in a nutshell is that tiny objects called elementary particles, instead of being what we think they are, a hectometer wide point with extremely small surface area, this is called the point particle theory, a way of looking at particles in extremely small type of matter. And another way this is known as, that is also known as the standard model. The universe would be made of 12 particles of matter, and then so they'd be split up into 3 categories. There would be quarks, as we talked about them. The types of quarks, what they'd be is that then there'd be up and down quarks, which would be the most stable types of quarks. There'd be charm and strange quarks. Strange quarks would be, instead of neutron stars, and then they'd be the most stable types of quarks on this list. And they also are the third lightest quark. Then there are charm quarks, which are inside of radioactive radiation, and then they also are known as supermassive neutrons. They are positively charged, by the way. So then they would be the third most massive. And then they are top and bottom quarks. Now these ones are quite heavy. As I've said before, they are many electric volts. Then as we get on to the other particles, like for instance, there would be the leptons. So then all the leptons, so first we need to start with, of course, there's electrons, and then there are muons. There are tau, there are electron neutrino, muon neutrino, tau neutrino. And of course there are anti-versions of these, but as said in Noether's theorem on supersymmetry, there may be a supersymmetric types of these particles, and that may make up this universe. Although it's not necessarily proven yet, but Noether was a very smart person, so she might be right on this. Now, it's not necessarily just because, she was smart, but I mean, even Einstein said in one of his letters that she is one of the smartest people that he has ever heard of or seen. Then we get on to the gauge bosons and scalar bosons. The gauge bosons would be a gluon, as we talked about before, the photon. Now, by the way, these photons would represent the 4th force of nature. There would be the gluon, which is a distributor of the strong force, a photon, that is a distributor of the electromagnetic force, which then splits off into a wave duality function, which then creates different types of probability amplitudes, which then would be different waves of one another. They'd be in this thing is called string duality. Then there'd be the Z and W boson, which basically just do not much, actually. They basically just do the distributing property of the gravitational field other than the gravitons. Then there'll be the one scalar boson known as the Higgs boson, which is what gives particles their mass and is a distributor of the Higgs field, otherwise known as the weak force. So anyways, but then let's imagine all these vibrating with one another. Different amplitations of these would create different types of vibrations with one another. They would create different types of weird and strange properties of one another that then would amplify them and then would turn them into different types of particles with respect to their vibrations. Now, even though a stringy universe is good, and even though some people it may even make some people a little bit hungry who are watching this video, well, we might have to check out this idea, even though this cosmic string theory. By the way, this theory was made of the co-host of string theory, which would be Supergiant. So anyways, now even though this theory is beautiful and splendid little theory, still it's not necessarily proven, as we could tell. See, so then we get on to brains, and we also get on to the higher dimensional Calabi-Yau manifold spaces. So then first we need to get on to brains and membranes. So basically a brain and membrane are basically just higher dimensional structures of the strings. What these strings would do is that then they would be vibrating their own unique way in different types of shapes, sizes, and even parts of Pythagoras' 5 perfect solids. So now, but then as we get up into higher and higher dimensions, they just become D2, D3, and D4 brains, and then they begin to form coupling. These coupling structures, what they do is that then they interact with one another. What these structures would do is that then they couple. This creates the black brain structure. These black brains, what they do is that so they are formed by coupling events. This means that so then there can be two different types of strings. There can be a closed string, and then there can be an open-ended string. What this open-ended string will do is that then there could be a particle that could raise it, and then could stretch it out, and then to put it into the black hole. Although, since because of the black brain event, this black brain will envelop with it, and then sort of become a weird part of it, almost like a fracture in glass. I know. And what this is literally is, although now in some cases these weird brains, which are in these things that, which are in these very, very strange indeed spaces, which would be called. Anyway, so what these spaces would be called is that they would be called Hilbert spaces that would envelop these weird brain structures in the form of bra and ket notations in these spaces. But another theory, which is still would save string theory, it would be the Calabi-Yau manifold spaces, multi-dimensional spaces that would then be vibrating one another in unique ways in the form of their unique non-Euclidean geometries. These non-Euclidean geometries would then let particles go over and under them in very unique ways that defy Euclid's 5 postulates. These are some very complex topics of black holes that we just talked about and how they work. And I am afraid that, well, this is the end of this video. I hope you like this video. And remember, keep on learning. Anyways, guys, well, I'll see you guys later. See ya.